There you go. I'm unmuted now. Welcome back, everyone. We're about ready to start. Looks like class has gotten kind of small attendance, but I'm glad that everyone that made it in has made it in today. Welcome back. And as far as what we have on the menu for the announcements today, biggest thing is what we talked about last class. We have our upcoming exam one. And just a quick reminder, I'll be working over the weekend on this block right here, filling out the exact coverage on exam one. With where we are on the pacing of the class, it looks like it's going to be chapters 1, 2, chapters 11, chapters 13. And I'll also be posting the review problems so you'll know what does an actual exam question look like when you go from using RStudio and the homework sets to just answering conceptual questions in the exam. So you'll have a great idea of what those questions are going to look like before we get into week number 4. Also, at the start of week number 4, probably the very first thing I'm going to be doing on Monday is sending a message to each individual student confirming your location to take the exam. I'll send instructions for if you're at the Pocatello Testing Center, how to schedule, Idaho Falls Testing Center, and so on. So that's our goal so far. We're going to be finishing off chapter 11 and starting a more abstract chapter, chapter 13. But any questions at all, folks, to start us out today? Okay, let's get started. We've got some pretty exciting topics to look into. Chapter 13 is going to contain the so-called central limit theorem of statistics. There'll be two versions of it. We're going to focus on the central limit theorem for quantitative data first. So when you do the reading on this chapter 13, if you want, you can just stop after considering the central limit theorem for the quantitative data. There'll be another central limit theorem for categorical data, but we'll loop back into that when we're about to do the inferential statistics for categorical data. But for the moment, we're practicing working with the normal distribution. So here's where we left off last Monday. So we're looking into a new problem where they made a measurement of the amount of time it takes people to react to a brake light. They said reaction time for an in-traffic response to a brake signal from a standard brake light can be modeled with a normal distribution using a mean of 1.25 seconds and a standard deviation of 0.46 seconds. 4 seconds would have been catastrophic. So a smaller standard deviation than stated. And these two values just came from the data itself in this article. So we're thinking the data probably had a format like this, maybe slightly more symmetric, or maybe even more rougher, maybe slightly more skew in one direction or the next. But they felt that the normal curve with the central value stated and its standard deviation still modeled well enough for the data obtained in that example. First thing we did was use this as a variable for the reaction time from a randomly selected person in that particular study. So we're just modeling the study itself. We wrote X is distributed normally, having a mean of 1.25 seconds, and a standard deviation of 0.46 seconds. And once we put that in the calculator, that was the immediate first thing that we declared. Mean is mu 1.25, sigma is 0.46. Then to answer this question, we want to know what's the probability of, look at that guide for what X is, randomly selecting one driver at this study and finding that the reaction time was between 1 second and 1.75 seconds. To do that probability, we cited the R syntax. I guess this will do. Here it is right here. P norm stands for probability in the normal distribution. We took 1.75 first, so that's the upper bound. And it's going to calculate all the area to the left of that using those two parameters. But since we're between two numbers, we also subtracted P norm at 1 second with the same parameter values. And then running all that syntax, that gave us for part A, let me see here, part B, rather, 0.5607. So we stayed there, rounded to 4 decimal places. And our interpretation was just a matter of reading out what X is, saying what values it was between, and either say the probability or the percent chance of that event occurring. We turned it around. Did the probability X is greater than 2? And the syntax is even nicer for this, but watch out for directionality. RStudio, on its natural basis, before you change any options, wants to compute areas to the left. So if you see a greater than 2, you can do this pretty quickly, either using the complement rule, 1 minus the p-norm, or just change this function value here, lower.tail, set to false. We'll often go this way since sometimes it makes more conceptual sense, even though the syntax is a little bit longer when you write it out. And same kind of interpretation. We got that in probability, so we said there's about a 5.15% chance a randomly selected driver takes over 2 seconds to respond to a brake light, which was a non-trivial probability. So that's where we left off before. The syntax has been pasted on the Word document, and now we're just going to build on it going into the next part, Part D. But any questions at all, folks, with the refresher on either of these problems? Okay, so far we've been solving these values right here, coming up with a probability, which makes Part D look quite a bit different out of nowhere. This one has the probability. It's given straight out as a 0.10, and the thing we're trying to find the value of is k this time. So we're solving for something totally different, a new unknown. Here we'll also give a practical interpretation like before. Let me just keep this parallel in the highlighter use. And our goal is to get the value of k. This one uses a different function in RStudio. To get a k value, when we have a probability statement like this, and a probability actually provided, we use k equals q norm. Inside q norm, the probability given on the right, we just input 0.10, or just 0.1 will do the job. Then we watch the directionality. That's a less than, so we're okay to not worry about lower.tail set to false. It'll be set to true, which is what we want on this problem. Next thing we'll put in is the values of the parameters. The mean is 1.25, standard deviation is 0.46. And this totally does the job for us. This will solve for the value k in this problem. So typing that out pretty much directly in RStudio, this is what it would look like. Q norm. Here, Q stands for quantile. So think in terms of quartiles or quantiles. Here, we're looking for the 0.10 quartile in the sense that all drivers are going to be, for whatever value k we find, 10% of them are going to be right at the k value or quicker, and 90% of them are going to be right at this value k or slower in their reaction time. But typing this in directly, we get 0.10 mu and sigma. Again, this is just a quality of life enhancement. If you declare mu and sigma, you can just retype it here, not worry about mistyping any of those numbers. Now, if you run this, let's keep in mind that the mean of the data is 1.25 seconds. Now here we're asking, what's the probability that the reaction time less than k is 0.10? So this should be pretty fast. It should be a lot less. If you run the syntax, here's what we get. This one's not a probability at all. This is a value that's inside. When you have something inside near x, its units are in seconds for these data. So we get, let's say rounding to 2 decimal places seems appropriate, 0.66 seconds. Then that solves the problem. The big challenge is, now that we've solved for k, is to give a quick practical interpretation of what we've just computed. And there's a lot of good interpretations that you could give for something like this. Let me put this on the next page so we can fit it all without squeezing it in. One pretty standard interpretation is just kind of unpack everything you see here exactly the same way we did the interpretation on this one in part C. If you go that route, you might have an interpretation that goes along these lines. There is go to the probability, 10% chance that the reaction time to the brake light is, well, when we did the last interpretation, let me see if I can show that. We said greater than 2 seconds. Here, we're doing the same thing, but K, we've solved and found to be 0.66 seconds. So we'll say is 0.66 seconds or less. We're saying or less because of the directionality, less than in the problem. So that's kind of nice in a certain sense. 10% of the drivers react pretty fast within less than a second, 0.66 seconds specifically. Different kind of problem. Sometimes we're looking for a value related to the variable, where it's the reaction time for the brake signal being between two values, greater than a value or less than a value. Other times we have the probability. We want to know what is the amount of time in seconds or whatever the unit might be that corresponds to the probability and the directionality given. So if that was a greater than, we'd have put in lower.tell equals false. We'd still get the same number, but our interpretation would have been completely different. We would have said there's a 90% chance that they react 0.66 seconds or longer. Well, that's the full write-up for this problem. We're going to do more of these just to get some practice with this, how it all works, comes together, and just to see different variations like on part D, for example. But any questions or comments at the moment? Okay, I think it's a good idea to just mention one more common interpretation to the part D we see here. So let me put this in a bracket, just say an additional solution. Another solution might have gone along these lines. If you see a less than directionality and a 10% chance, you can say the quickest 10% of drivers, by quickest we mean responding to a brake light, reacts, go to the value, 0.66 seconds or less. I kind of like that interpretation because it really gives you the impact of what you're saying here. These are all the faster drivers. We said it in the same way in purple, but it feels different when you compare this response versus the one down here. Any version's completely fine, but another good thing about this one is sometimes questions are posed this way. We have to come up with the probability statement and solve. So if you see a statement posed in this kind of way, it might remind you all this is saying is solve that probability statement there. Well, let me share the syntax with the solution to all these. So here it is finally updated. And now we'll move on to the full write-up for all the R syntax as it relates to the normal distribution, and then look into one additional problem. But any last questions or comments, folks, before we go on to the next? Okay, so coming down here, I have this file or this work or these formulas here duplicate as a file called R syntax, just for an easy reference. That way you don't have to necessarily dig through the entire chapter notes to find this resource sheet right here. And what this conveys is any computation that might come up with the normal probability model in this course. So R syntax for anything that comes up, when your random variable is distributed normally with the mean mu, standard deviation sigma, gives us these 5 different values. So if you're finding a probability less than, your p-norm function looks like this. If you do probability greater than, p-norm function is almost the same, but you have lower.tail set to false. Let's match up the highlighting that we used last time. So watch out for these directionalities. They can cause some problem in the syntax if we miss it. This is the clunky one in RStudio. If you're finding the probability x is between two numbers, you need to take the upper number B, compute P norm B, pass the parameters mu sigma, then put the lower number here, minus P norm A mu sigma. So that's the one we started off with, our very first P norm function. And finally, the Q norm is the last problem that we just did, and there's two versions of that as well. We did this version. We were trying to solve probability x less than a equals some given probability. We just throw the probability inside, compute Q norm P mu sigma, and that gives us the value a inside the function there. 5 is essentially the same, but the directionality is the important thing. This is for x less than a specific number, where you're solving for that number a. But if you change this around, I want to solve probability x is greater than a number. Don't forget to flip lower.tail set to false. It always defaults as true. And then you'll get the right value that you're expecting. So that's a lot of stuff altogether. And one thing that we will do just on the next problem, in case it's a handy way to organize the information, is sometimes when you're doing probability computations, even when you've done a lot of them, it's not a bad idea to just draw a picture. Sometimes people who are considered PhD experts in statistics and probabilities, they just draw the picture to organize everything in their mind and make sure that the values they get, say 0.66 seconds, passes the smell test essentially, that the number really makes sense in the picture you drew. Sometimes that's a really good strategy, so we'll practice that on the next problem. But while we're at it, let's practice it right here. Let's suppose you're trying to solve this. Probability x less than -2. If you're trying to come up with that probability, your probability is going to be an area that's going to start right here at -2. And in the graph, if you so chose to draw it, the shading would look like this. This is kind of tricky shading because it doesn't go below the x-axis, and my x-axis is kind of higher than it actually looks. So keep that in mind in the interpretation of this area. So for example, this one challenge that I didn't quite get right in my code is that there's a actual x-axis going like this. It's hard to draw a perfectly good x-axis that way. Let me just drop it a little bit. Okay, let's let that be the x-axis so we can just be more specific when we say shading. The shading doesn't actually dip below that x-axis, so that's a better way to convey it. If you want to get that probability, all you would write in is, this is P norm, put in -2, the value for mu, the value for sigma, and that's exactly what that area is going to be as well. That might be too many arrows, so let me convey it that way. So on the graph, this is what it looks like. And if we're doing a Q norm function, sometimes those are more confusing because Q norm gives you the unknown that we're used to finding. It gives you the actual probability, which is that area there. So let's say you're doing something along these lines. Probability x greater than some value k is equal to, let's say it's 0.3. So we already know the probability, but the question is, what is k equal to? We can put that on the graph as well. What we would want to put on the graph is an area 0.3, but we also have to pay attention to the directionality. This is a greater than, so we're shading area to the right now on this one. So to my eye, I'm going to try to put where I think 30% of the area is under the normal curve. It would be maybe right around here. Definitely not perfect, but let's say it's about here. This is area equals 0.3, coming from the probability statement down below here. The thing we're trying to solve is, what is k? But k can be solved pretty quickly. K is equal to Q norm, passed to the Q norm function, the probability that was provided on the onset, 0.3, then go mu sigma, but watch out for that directionality. Here we have to flip lower dot tail equals false. So let's write that in. Lower dot tail equals false. So visually, this is what the Q norm and P norm functions are doing for two quick examples. And again, we'll adopt this approach when we analyze the last probabilities on these nodes. But any questions or comments at the moment? Okay, so next problem is kind of relevant to us in context. It's all about snowfall. We're going to be looking specifically into Rochester, New York. We're told for some pretty basic statistics. This is from a book that's a little bit older, so I think these might be slightly better estimated. But the values I took were in Rochester, New York, for the month of December, on average, they get 21.9 inches of snowfall, which is quite a lot. We got what feels like 0 inches of snowfall, depending on where in Idaho you're based in. But the value they're stating for a parameter here is U equals 21.9 inches. We get even more information. The mean is never the full story. We want to know how spread out are these snowfall events across different years in December in this area. And they tell us the standard deviation is 6.5 inches. So we have a value for sigma as well. And I looked this up just today because I know that some crazy stuff is going on in the news with the polar vortex. What happened in December 2025, I just added this morning, they got 37.8 inches of snow, which is like catastrophic practically when we see these values. Or is it? We're going to be able to analyze that. How rare is last year to 2025 37.8 inches of snow? That sounds like a snow apocalypse almost in Rochester, New York. We'll run through the problem, but first notice this statement has already been provided. But this could be a question in and of itself. This is the sampling distribution. Of X. That was the very first problem that we answered when we were in example 3. And you'll see these kinds of things when they come up in the homework. This could be an exam question as well. What is the probability distribution of X? But essentially all we're doing is we're using the model they gave us. Follows a normal distribution, so there's n. We pass to the normal distribution the parameter values, 21.9 provided, and 6.5 in units of inches. And so we're just filling out that information. And you can always answer this in ordinary words. X, the amount of snowfall in Rochester, New York in December of this year, is distributed normally with a mean of 21.9 and 6.5 inches. You know, actually, I would want to change this up. Now that I'm reading this wording, I think that this probably can be improved in its wording quite a bit. I don't like this year statement. So sorry for a quick edit on this one, just to make this a more sensible variable X. Let's say X is the amount of snowfall in Rochester in December of randomly selected year. That's going to make this be an accurate statement for a probability model. Again, that wording was strange. Sorry about that. That missed my proofreading this morning. The reason we want to say a randomly selected year is because we say of this year, we already know the value. There's no probabilities to compute. It's either 37.8 as true, what they actually got. And if it doesn't come out to that value, we'd say false. And so it's impossible to get that number. So sorry for the correction here. We're thinking December's across quite a few years, not just one in particular. So that's a probability model so far. And here are what the questions are going to look like. Notice they're kind of backwards with what we did in example 3. Example 3 had a probability statement. Probability X less than some number, for example, we want to find. But this one is asking us to include the probability statement. So this is a skill we'll practice in the homework as well. It could become an exam question in its own right. And essentially, this is the question. The question is itself the practical interpretation. So we're going backwards now, and we're writing down to start off this problem. When you see include the probability statement in your answer, we mean this, right? The probability that X, we bring in the variable X, now corrected to be a proper random variable. It says experience 10 inches of snowfall or less. So we'll say less than 10 inches. And there's actually two equivalent answers to this. Because like we mentioned, when we were talking about concepts with the normal distribution, your probability is exactly the same if you put less than or equals. This one says 10 inches, so equal to 10 inches or less. So that's probably the better way to write it. But I'm pretty forgiving on that because your probability is exactly the same if you put strictly less than, comes out to the same value for the normal distribution. But still, I'll convey it this way just because it seems to be more parallel to the statement above if we write it that way. So we want probability X less than or equal to 10. And here's the picture that goes along with this. There's a normal distribution. The horizontal axis is snowfall in inches, so I'll just write inches as a reminder. This is N, 21.9. 6.5, that's just the parameter values stated from this part right here down below. But that's important because it tells us 21.9 goes here. And if we're saying less than or equal to 10 inches, we know that's kind of far away. Standard deviation is about 6.5, so we are around 10 inches. We don't have to compute this exactly, but we know we're somewhere out here, somewhat far off to the left. I'll put it here for a pretty rough graph. So the point of the graph is to not put everything exactly where it should be, but to just give us some idea of how big is this probability. So I know if I know 10 inches goes here, and I get a probability that's say 40% or 0.60, 60%, I know that's not right. It's got to be less than 50% because it's to the left of the center, 21.9. But now to solve this is pretty fast. We'll bring this all into the calculator. Starting with the parameter values, mu gets the value 21.9. Sigma will get the value 6.5. I'll put that hash to just put in a comment that this is part A. And now to do this probability, we'll just type in P norm, 10 to come from this 10 right here, mu sigma. And that totally does the job. Now, when we run this, we're expecting a small probability. So let's see if that happens. Hit Control A, Control Enter. And yeah, that comes out as 0.0336 upon rounding. So 0.0336. Seems about right for this value here. And at this stage, we're totally we're totally done. We don't have to give a practical interpretation because the practical interpretation is the question itself. But if you did, it's no harm. If you put it in your own words that this means the amount of snowfall in a randomly selected month of December in Rochester, New York, being below 10 inches will occur about 3.36% of the time. If you said that, there's no harm done there. But for this kind of question, our work would be completely done right at that step. So that's what the method looked like. That's the probability we got and the picture that goes along with it. Any questions whatsoever, folks, getting through this one? Okay, so let me know if any kind of weird things occur with your syntax as normal when you're doing this in the homework. I'll be very happy to help. You could literally just copy this if you like, paste it into the email and ask me what's going on with my syntax if you get an error, and I'll be very happy to look into it and diagnose it with you. But moving on to part B. Again, the major thing with this problem is that it's backwards. Example 3 started with the probability statement, and once we got the probability, we did the practical interpretation. This time, we have the interpretation of what we want, but we must provide the probability statement. So we must do this in the homework as well. It means we start with probability of something that's going to involve the variable x, amount of snowfall in December for Rochester, New York, in a randomly selected year. They're asking, what is the probability that Rochester will experience between? If you see the word between, that automatically means you're looking into this kind of probability statement. So the random variable x is constrained between a lower value and an upper value. That will be the 10 inches and the 20 inches in the problem. So 10 and 20 will go inside here. And now we're just about on our way. Let's do another quick graph on this one, just to organize what we're seeing. I'll put just the center this time, 21.9. But putting a unit on the axis, it definitely just reminds us, what are we really looking into? What is the context? Helps us make sense of the numbers as we put them down. We're going from a lower bound of 10 inches, so about right here, we're copying the last graph. But this time we're shading to the right, all the way up to 20 inches, pretty close to that 21.9. So about right here, we want this area. All I can say for certain based on the graph is it's less than 50%. Exactly 50% would be 21.9, and to the left without stopping at any value. But here's where the 10 inches went, and the 20 inches. So probably I would guess something around 30 to 40% if I was having to make a wild guess on this one. But we don't have to guess. Our studio is going to compute this exactly and very cleanly, just on like on the last problem. But this is the one that has this kind of syntax coming up. We're doing a random variable x between two values, so we have to write out p-norm twice this time. The major thing to remind yourself is when you write p-norm twice, do the upper bound first. But you know, if you got it backwards, you're going to get a negative number, and you'll know negative numbers do not make sense as probabilities or percents in this context. So we'll just take off the negative sign and it's actually correct. But to avoid the confusion of a negative value for the probability, let's make sure we put it in this way. Starting with the upper value 20, let's call this part B, p-norm, 20 mu sigma, then go minus p-norm, 10 mu sigma. So once again, we're pretty much just putting in values that we see here on line 3 for this quick set of notes. We run this, hit Control A, Control Enter. Ignore the part A side, we're getting the value in part B. Let me just make that a little bit bigger. Even bigger still, there we go. That's our number, 0.3515. We'll throw that on the notes, but any questions at the moment, folks, getting that value? Okay, so about a 35% chance of getting between 10 and 20 inches of snowfall this year is what it's saying. So 0.3515. And our work is done the moment we put down that number. You don't have to put down the graph, but if you find it's useful, no harm done in doing so. Now, here's the interesting one. We did two p-norm functions on both of these, and this one is a q-norm question. We can tell this is a q-norm question right away, but when it said 1%, they provided us a probability straight out, and so this is a great way to think about this problem before we even get started. That 1% of worst cases, we'll think of this as being a probability 0.01, or excuse me, let me try again on my percents. 10 is the actual percent or the actual decimal number. Or hang on, no, I think I just didn't drink enough coffee today. 0.01, after debating myself a little bit over that. Decimal shifting was just a little hard for me today. They move the decimal 2 points to the right, you get back to the 1%. So we have probability 0.01 we're dealing with. It's also tricky because we're trying to say what is a worst case. And that's kind of open to interpretation depending on the person. Maybe some people just absolutely love snow and they're heartbroken. There's not a lot of snow around locally for snowboarding and things like that. So you might think worst cases is very low amount of snowfall. But I think in this context, worst case means huge amounts of snowfall. I'll try not to write these kind of questions on homework that are open to interpretation. So if this was a homework question, I would be more specific on what do we mean by worst case. But again, let's think of heavy amount of snowfall is what's meant there. First thing we'll do is write down the probability statement as before. Then we'll do a picture and run the syntax. So probability statement on this one is probability variable x. Now, when it said worst case, I'm going to think of this. X is the amount of snowfall, and it's going to be greater than some value, k, which we're going to solve for. We know the probability. It was given as a 1%, which must be converted to a decimal, so put in 0.01. And that's a probability statement on this problem. Because of that greater than, we have to be mindful of lower.tail set to false when we run our syntax. But also here's now the picture that goes along with this. Same kind of normal curve as always. Doesn't have to be perfectly drawn, but let's put in 21.9 here, the mean or center. Value for k, we're saying the probability for x greater than k is 0.01. So 1% of the area is to the right of k. K is probably somewhere pretty far over here. I'm not trying to put it down exactly, but try to put it in the rough relative place it should be, somewhere far to the right. So here we have area, or probability, 0.01. Well, that's the organization so far. Now, when we look at it from the R syntax side, let's ignore that for just a moment. In the R syntax, we're doing 5 here. We're trying to solve probability. X is larger than some value A. We wrote down K in our notes, equals our probability. So we'll cite Q norm past the probability. And the only danger on this is don't forget lower.tail is false. But if you did forget and you get a weird value for K, the picture will help. It'll tell you that K is absolutely not in the right spot because the number is just not going to make sense. So if I was typing this in RStudio and I wasn't being super careful about the direction or where K was located, I might type it out this way. Part C, Q norm, because we're solving for the value inside the probability statement. Q norm takes a probability, 0.01, then just pass the same parameters, mu, sigma. And we know we need to put in more, but let me show you what it would look like if we ran it just like that. Hit Control A, Control Enter, and it says for the output, 6.77. Now, don't forget the unit here is inches of snow. And if we're interpreting worst case to be lots and lots of snow, there's no way that's 6.77 inches. We're expecting K to be around, say, 30 inches or in that neighborhood. The thing that was missing is the directionality. We have to also include in our syntax lower.tail equals false. So when we run that one more time with the fix, we get 37.02 inches. And that looks about right on the diagram. K is far to the right when there's only 0.01 area to the right of it. So we'll cite our value. Again, use what seems about natural and reasonable for rounding. I'd say 1 or 2 decimal places is reasonable in this problem. Let's go with 37.02 inches. So K equals 37.02 inches. That's the amount of snowfall that describes the 1% worst cases for the month of December. And to put that in context, they had more. They had 37.8 inches in 2025. Well, that's the conclusion of this problem so far. Maybe one big takeaway is don't forget that these are probability models. And the performance of this model is how well a normal curve fits the actual population data. The population needs to be symmetric, mound shaped. And if that observation is not true, then the normal model fails. But even more goes into this. We cited specific parameter values, 21.9, 6.5. If one or both of those are off, that's enough to make this model perform badly. So maybe this isn't too surprising. Maybe what's going on is the model that we're using in this problem doesn't fit New York City too well any longer. Maybe it was good for historical data in the 80s, 90s, maybe even the 2000s. But in 2025, maybe those parameters have to be adjusted to say what's typical for Rochester, New York. But going by the model, that's a pretty interesting thing that happened just last year. Well, any last questions or takeaway comments, folks, on the conclusion of Chapter 11, Normal Distributions? Okay, well, once again, for any section where we use RStudio, always have a paper trail here. So when you're going to do the homework assignment, I'm a fan of parallelism. The problems you'll see in the homework are pretty similar to the ones we did here. And you can match up some of these kind of problems to see how it will go, make adjustments in your syntax. And don't ever hesitate to reach out if errors or issues occur. I'll be happy to help out. But let's save this. This will be uploaded in Canvas after class. And now we're going into chapter 13, where we'll continue to use normal distributions. But now the major concept in chapter 13 is, how does probability, working with normal models, allow us to do inferential statistics? By inferential statistics, what we mean is, how do we make statements that are accurate about a population and also include a degree of the accuracy or reliability or margin of error based purely on sample data? Chapter 13 is going to answer that question for us through the central limit theorem. But let's close this up and start taking a look. Chapter 13 will probably finish when we come back on Monday of class next week. And to start it out, we have a couple of just interesting topics and some review information to think about as we go before we delve into, let me show you in the notes, the big idea. The biggest idea in this notes is this theorem right here, the central limit theorem. It says if we gather a simple random sample, and we'll do some work just saying exactly what we mean by that, from any population, as long as that population has a finite mean and a standard deviation, then for large enough values of n, the sample size, the sampling distribution of your mean, the sample mean x bar, follows this normal model with that particular parameter for the mean and that particular parameter for the standard deviation, sigma divided by square root of n. And that's a really big statement once we start to really break it down, what exactly it's saying. So this is possibly the most abstract work we're going to do in the entire course, the entire textbook, is through this theorem. So to start off, we're really going to begin by just refreshing what we mean by parameters and talking about simple random samples. So let's go back to the top of the notes. And this is how we started off the course as well. We have the dichotomy of population versus the sample, and then again with parameter versus the statistic. So the population is the entire collection of all individuals that we're concerned about. And so in this example, the population would be all ISU students. Let's say all students currently registered for this semester. A sample is just a subset of the underlying population. So if we want to look into a parameter that describes a population, say that parameter is the mean GPA of all ISU students, we could find that by taking a sample. Let's think about this for just a moment. If you work for ISU, if you are maybe working for the registrar's office, they possibly have the tools and the database to just compute this. So they don't need to take a simple random sample. They just put in some lines of code in their database and they get the number out. So why would anyone want to do this study? Well, imagine you're a competing college, maybe a college in Utah, Washington, and so on, maybe an online college. and maybe you're trying to get students from ISU to register for your university. If that's the case, you probably want that value, and you can't just call ISU and have them tell you what is the average GPA for all ISU students over the phone. That's like a trade secret. They're not going to give you that up. But if you have a way of collecting a sample of all ISU students, if the sample is representative of the underlying population, then you can calculate a statistic. The statistic describes a sample, and so that's what X bar is going to be. We'll assume a researcher external to ISU. For that researcher, mu is unknown. They gathered a simple random sample of size 100 from the underlying population, and now they have the sample mean X bar. The great thing about this statistic is it is an unbiased, very accurate estimator for the parameter that's unknown to them. And so here's the statement. If they want to estimate mu, it'll be approximately equal to X bar, provided our sample is representative of the entire population of ISU students. But there's some big trouble here. One massive issue, the reason this is a 16-week semester, is that this estimation right here is essentially useless unless we do one big critical thing after writing down the parameter mean for all ISU students is approximately equal to the sample mean. This is useless unless we describe the reliability, the error, or the margin of error in making that estimate. So we must describe the margin of error in this estimate. So that's one major challenge. You can't just say something is approximately equal to something else and have that be useful until we know the reliability of that estimate in the very first place. That's a question we'll answer through confidence intervals when we're in chapter 14. And there's even other challenges. They can't just say, for example, take a gathering of 100 students from the Pocatello main campus or from one particular college at Pocatello. It has to really represent all ISU students, and that's a really, really big category of students. Some of them are graduate level, some of them are undergraduate, some of them are fully online, some of them are on far remote campuses like Meridian. These 100 students have to represent well everybody. So the next question is, how do you know you have a representative sample in the very first place? And there's lots of various tools that can help us out with that kind of question. But the golden standard, the one that works for all of the statistical methods we'll describe in this book, is the so-called simple random sample. Well, any questions or comments so far, folks? Thinking about this really kind of small capsule example with what we're about to do? Okay, so let's answer what is a simple random sample. Our author often uses SRS to stand for simple random sample. I'll usually just write it out. It doesn't take that much time. Less acronyms are sometimes better. A simple random sample of size n is a sample. It has to be selected in a way such that every set of n individuals from the population has an equal chance of being selected. So in a certain sense, we've eliminated any possibility of bias. It's possible when we select a simple random sample of 100 students, there might be a bias in that sample, but the process itself is minimizing the chance of that occurring. So this gives us the highest degree of reliability that the sample we selected has the best chance of being representative of all ISU students. Now you might wonder, how do you take a simple random sample of all ISU students? You have to have a way of describing them. An index number, say a student number, student ID number. So you need to produce a database for some index, some identifier variable, maybe the student number, for every single ISU student. So this is a pretty big problem. But once you have that database collected, you can simulate taking a simple random sample in a pretty rapid way. And that's what we'll describe in the example down below. So we're going to simulate this whole thing inside RStudio. We'll make the problem a little smaller. We're going to simulate the process of taking a simple random sample of size 20 from some population of size 1,000. Any questions at all, folks, before we go to give this a try? Okay, so in RStudio, let's get working on this task. Probably need a slightly bigger field here. It's always difficult to get the windows just right. I think that'll do it for us. I'll make this a little smaller because we're going to focus on the graphs as well as we go to write this out. And very first thing is, let's say we have a population size 1,000, and this can be any population whatsoever, but we just talked about the normal distribution. So let's select a sample of size or grab a population of size 1,000 by selecting them randomly from the normal distribution. So here we'll say, define the population, and let's call this just literally population. Gets the output of, I want to take a random sample, so I'll start with lowercase r. I want it to come from the normal distribution, so I'll type in norm. It asks for us to supply a value n. N is going to be the size of this population, so I'll pass to it 1,000. And this can be anything. To make it kind of generic, I'll just put in some random mean. Let's say a mean 100. Who knows what this might represent? Not necessarily GPAs or ISU any longer. I'll put a standard deviation of 10, and that'll be our population. I'm just going to run this once. If I run this syntax again, I'm going to swap out the population, but I want that to be that population for us for all time. So I'm going to put a comment right here so that now when I run the syntax, it's not going to run through this any longer. My population, if I hit Control-A, Control-Enter, is frozen and fixed. And if you wanted to do population, just backspace, run it again, and it'll swap out the population for a brand new one. So let me put the hash back in, Shift 3. So we've got a population, and if we type down here in the console, population, hit enter, there they are. 996 tells us we're indexing through 996, 7, 8, 9, 1,000. So that's what the bracketed values are on the left. And these are the population values on the right. I can't really get a sense for what this looks like scrolling through here. So first thing we'll do is produce graphics for this population. We'll go hist to stand for histogram, like before. Put in population. I'll delete the main title. That's just a personal choice. Once again, you can leave it in if you prefer. Hit Control-A, Control-Enter, and that's our population. It's a sample of size 1,000, and it came from a population that was normally distributed. And R does a very, very good job of simulating a true normal distribution and sampling randomly from that. And that looks about right. If you were to draw a normal curve to this, sure, it does seem a little bit off. The main peak is not exactly at 100. It's a little bit slightly to the left, but it's not so pronounced. It looks like it has that nice mound or bell-shaped curve and one main peak, just slightly off center. It's off center because it was a random sample, and so there's random variability as well that comes in. Well, we've got a population so far. Now the big question we want to delve into is, what would a simple random sample look like if we take a simple random sample of size 20 from that as a population? So that's not too bad to put in. But it might be a good idea to put in both a histogram for the population and another one for the sample. So let me put in one random line of syntax here. Let's describe what it is because it does look pretty random. This will give us not side-by-side displays. I want to put a display above and below. Gives two displays above and below. That allows us to compare the population with the sample we take as histograms all on one screen. And again, the syntax is random. It goes par mf row equals C. I want 2 rows, 1 column, so 2, 1. Pretty random bit of syntax. You'll never have to use that unless you just find it's convenient. And you can always find it here if this comes up. So that'll give us 2 displays, one above, one below. We might have to resize this window a little bit. Now let's go get the sample of size 20. I'll call this X. X gets. If you want a random sample from, say, this population right here, you just write in sample, put in the thing you're sampling from, its population. The next input is going to be the size 20. Replace false means I won't have someone appearing in the sample twice. Once someone's been selected, they're eliminated from this roster, and it samples from the reduced roster. So no duplicates inside. That'll be our random sample. So let's see if this comes out right. Hit Control A, Control Enter. And yeah, here's X, 20 individuals from the population. And now I need to resize the window a little bit better, it's telling me. So this just means the size wasn't big enough. So let me run it again. I want to put the sample down below, so that's going to be hist X, where we contain the sample. Main is eliminated. Let's put for X label sample, just so we know exactly what we're looking into. Then finally hit Control A and Control Enter. And this did the job for us. Let me see if I can make that even slightly better looking. Pretty weird sample, right? Our underlying population was nice. It looks very, very normally distributed, only just some small issues with it. But when we selected a sample of size 20 from that original population, here's what we got. It's kind of strange, ugly looking data. It is unimodal in the sense that there's one main peak, but it has a lot of data going off to the left. It's just weird looking. You know, that's a side effect of taking a sample of size 20. And it's kind of unfortunate because statistical designs are sometimes expensive. Sometimes doing a sample of size 20 takes a lot of cash to do, depending on what the study is. So sometimes we have small sample sizes, and there's nothing we can do about it. But there's sampling variability as well. So if you rerun this, hit Control A, Control Enter, that's the next sample. It changes a lot. Now it seems to have some weird things going on to the right, still unimodal. And every single time you run this, you get a different picture. But notice every time we do this, the mean seems to be pretty close to the true mean. The spread, you know, a little bit off on this one, but within the same ballpark of the original spread of the problem. This sample is a simple random sample of this population in the sense that every sample of size 20 coming from a population of size 1,000 has very, very close to exactly the same equal chance of occurring. Let's run this some more just to see what can happen. Hit Control Enter again. And that's not too bad. If you were doing, say, a capstone project for maybe a biology or engineering course and you had random data, if this is your data, people would be very happy. It's at least roughly symmetric, some skew more to the right, but that's okay. We can work with this. Run it again and looks a little bit more problematic, but again, that's not too bad. Some more skew to the left, but these samples are typical when the sample size is so small. And let's see how weird it gets. That's pretty bad. It has almost like a sawtooth shape. Some people might say there's a main peak here, 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 so 4 modes. There's bimodal for 2 main peaks, 1 unimodal for 1 main peak, but this would be 4 modes altogether. But is it unusual? Not really for sample size 20. If you want something cleaner, you might have to go to sample size 100. And, oh, that's a letter, not a number. Once you get to sample size 100, things start to stabilize. We can still get weird shapes like skew and such, multiple modes. But by and large, it starts to look cleaner and cleaner at higher sample sizes. But let's let this be our last picture. So the population never changed because we froze that line right there. And this will be our final thing to write down, the final sample. So this is what it looks like if you're simulating a random sample. For trying to do ISU, you now need your population to be all student ID numbers. But then this would do the job. It would take a simple random sample, a very great approximation of what that really is mathematically, of whichever size you select. So putting that all down, here's what it looks like for the syntax. And I'm noticing some typos. There we go. Let's fix that there. Not major because it was just a comment. And here's the actual graphics for the sample that we got. Well, the one we landed on. So there it is, folks. That's our quick, fast simulation for the process of taking a simple random sample. I think it should go on the next page. That graph is just a little too large. Because simple random sample is a concept that comes up as a condition to essentially every single statistical method we're going to look into. It can be weakened a little bit, but we'll discuss that when we get into those problems. It's good to see what does it actually look like if we simulate it in RStudio. We'll be looking into a different simulation in this chapter as well for the central limit theorem itself. But any last questions at all, folks, with just thinking about this one?
You run that population part each time, will that affect it, or is there a reason you commented it out?
Yeah, it'll affect it, but not in a big way. So if I left it like this, what'll happen is this population will change every single time. Yeah. So I want to think of it as one definite population, but you know it's going to be the same kind of concept. Run it like this. Population changed a little bit, and now that's the sample size 20 from the new population. Let's see if we can make this weird, though. If I get a really strange looking underlying population, sometimes it takes a lot of tries because that's a high population size, 1,000. Dang, I thought I had a good one, but I wanted it to be worse. You know, they're all just about the same. This one's pretty clean. Looks like, I would say one main peak if there's a tie there. So the main peak is somewhere right around here. The sample was pretty bizarre on this one. Other questions at the moment? Okay, thanks for asking about that. So the next part of the notes are just a place to collect a lot of different things that we're going to be analyzing, the various parameters and the various statistics we'll be seeing so far in this course. So think of this as just a one-stop location to define what is the sample mean? Is it a statistic or a parameter? What's the population mean? Mu. So these are all objects we've defined and looked in before. Formulas are down just for the sake of completeness. And on the right column, this is some parameters we're going to be looking into as well. For the moment, we're going to be focusing on quantitative data for quite a bit. But once we get into chapter, I believe, 19, chapter 20, we'll start looking into these parameters, the population proportion of successes and the sample proportion of successes, P for the parameter, P hat for the statistic. So that's what this page is all about. And down below is just a reminder that populations are often indexed or defined in terms of parameters, such as the normal model is defined in terms of the parameter mu and sigma. And this is really the first kind of homework question that occurs in chapter 13. This one's a tricky one to get into, so we'll take our time with it. But any questions, folks, with just a roundup of notations and symbols here? Okay, so here's our example one. Our goal here is to say, what is the statistic? What is the parameter? We'll use the correct symbols for both when we read through this. But these things tend to go kind of tricky, so let's again take our time. It starts by saying, after hearing of the national result that 44% of students engage in binge drinking, defined in this way, 5 drinks or more in one sitting for men, 4 or more for women, a university administrator surveys a random sample of 244 students. So we have a random sample N at size 244. They didn't say what kind of random sample, so we just hope it was a great sampling design, say a simple random sample. They sampled at one particular college and found that 96 of them admitted to binge drinking in the past week. This data is different than we've been looking into. It's categorical. There's no unit in terms of, say, time, inches of snowfall, anything along those lines. We're just saying out of 244 people, we categorize them to either not admitting to binge drinking, that would be a failure, and in fact admitting to binge drinking, in the line of statistics, that would have been a success, even though binge drinking doesn't sound like a success by any measure. That's a success because it seems to be what the study is all about, binge drinking. We had a national result, and we also had a sample coming from a particular college. So in this problem, we would say that there are 96 successes and this is categorical data. Everyone is either put in one category, a success, you've admitted to binge drinking when you were interviewed, or a failure, you did not admit to binge drinking. That word admitted is kind of strong there. I think it's good to include every time we say it. Well, we want to determine what's the statistic and what's the parameter. Let's maybe start with the parameter. The parameter describes the population, and anyone see what it might be? Yeah, good call. It definitely is tricky, but you're right. This right here is a parameter, absolutely. It's describing all students. We're assuming that these are college students. I'm assuming that these are college students, but it might include, say, high school as well. They would have to tell us more about the study. So with a very short description of the problem, that's the best we can go on. But you know what's crazy about this problem? What makes it really tricky is there are two parameters. There was the one that was given. So if you went to answer this question by saying P equals 0.44 is a parameter, that's about right because it's a national result. It describes a population of all college students. Well, let's put a little symbol on it. Let's call it P naught because there's another parameter in the background on this one. So let's think about that as we go to the statistic. P naught is going to be the proportion, or you could say percentage if it's 44%, or you could say it's the probability as 0.44 of a randomly selected student engaging in binge drinking. But what about for the sample? That's where the successes and the sample size come into play. And that's where we use this definition for the statistic. The statistic we added a symbol. We can say P hat equals 96 successes divided by the sample size of 244 students at that particular college is the statistic. So it is the statistic, sorry, because it came from a sample, and a statistic always describes a sample in the very first place. And it was just a different way we computed the statistic, the proportion or percent or probability, if you prefer to say, of people admitting to binge drinking. But look at where the actual sample came from. A university administrator surveyed a random sample of 244 students at his college. That implies something extremely important about this study. There's a national result that we're comparing that statistic to, but the actual parameter that this administrator is going to be very keen on trying to determine is not the P naught. It's a whole new parameter. There's a different population. There's the entire national population of all college students and potentially high school students, but There is the smaller population we're comparing it against, all the college students at this particular university, say ISU for an immediate, more relative example. So another parameter, this is the one being estimated is P equals the proportion of all students admitting to binge drinking at this specific university. Say again, ISU. We're comparing ISU against the national value, 44%. And so that means the thing that we're really trying to estimate is actually unknown. We don't have a value for that. We just have the national value. And that's just an estimate too. We're not saying it's exactly 0.44. They just provided us an estimate of it. So P is unknown. But there's more to that story. We can also say P, the proportion of all students admitting to binge drinking, is approximately equal to the statistic P hat. Let's put a value down to that. So that's a big screen all of a sudden. Take 96, divide by 244. And for some reason that didn't work. Let me try again. There we go. Comes out as 0.3934. And I'm not too worried about the format. If you call this 39.34%, that's just fine. Just be worried about if you're using it as a formula. You want it as a decimal value there, not a percentage. So we have an estimate, and that looks great. The university administrator might be excited because they might report, hey, we're below the national value, 44%. But that's a dangerous assertion too, because that estimate, recall, is useless until we describe the margin of error in making that estimate. We cannot at any point right here and now make a claim that this particular one university, say ISU, has less people engaging in binge drinking. We don't know until we actually find the margin of error there. So just as a reminder, because this is the big and dangerous idea about statistics, maybe red's a little too strong there. This estimate is useless until we describe the margin of error. So in the homework problem, it's more about just determine what the parameter is in the statistic. But the sidelong thought here is more about what we're going to be doing on once we get into, the full-on statistical methods starting in chapter 14. Well, any last questions, folks? Thinking about random samples, parameters, and statistics? Okay, well, have a great weekend, everyone. When we come back on Monday, our work is to understand that picture. This is essentially the central limit theorem visually. And we'll look into it in different ways as well to get a good conceptual idea of what's going on with this theorem. All the work we've done so far, it just sets the stage of that statement. But have a great weekend, folks. We'll be back to this part of the notes on Monday.